The next thing we are going to look at in rotation is the concept of rotational energy. The nice thing about this particular topic is that we're not really going to be learning a lot of new material when it comes to energy. It's simply going to be an addition to the concepts of energy that we've already learned earlier in the year. When we did linear motion, we talked about kinetic energy. You may or may not recall that there was actually a longer name for this called translational kinetic energy. If you think of translations in your geometry class, that was moving a shape linearly from one point A to another point B. And that's where the name translational kinetic energy comes from, in that we are moving an object from point A linearly to another point B. So the formula for that was that translational kinetic energy is equal to 1/2 mv squared. Note on your AP formula sheet that they don't include the T in this formula. You just need to know that it's a kinetic energy, and this is the particular formula that you use for linear motion. When we look at rotational motion, an object that is rotating may not be moving linearly from a point A over to a point B. It may just be rotating about an axis. So if you think about your ceiling fan, as it spins, the object is staying in the same spot attached to your ceiling, but the blades are spinning about that pivot point. Therefore, the mass in the blades is moving and therefore has kinetic energy. But we need to calculate that kinetic energy a little bit differently than we did for linear motion. However, the formula is going to look very similar to the old formula, and we're simply going to look at the rotational equivalence of the variables. So, instead of looking at the mass, or just the mass of the object, now we need to look at the rotational inertia, I, for the object. Keep in mind that you may have to use some version of I equal to some fraction multiplied by mr squared, or possibly the length squared. Then, instead of looking at the linear speed of the object, we would be looking at the angular speed of the object in squaring that. This might be a good place to remind you guys that we can find a relationship between the linear speed and the angular speed by doing the velocity equals omega multiplied by r, where r is the distance from the point to the pivot point. It's a useful formula to know for the AP test. It's not on your AP formula sheet. And since you get to bring your own AP formula sheet to the test this year, I'm going to encourage you to add that to your AP formula sheet. The most important thing that we talked about in the world of energy was the law of conservation of energy. And the nice thing here is we're not changing that. We had the law of conservation of energy when we did linear motion that said if you added up the total energy in a system and there were no outside forces, the total energy of the system should stay the same. Well, rotational energy is just another type of energy. And still, if we look at the total energy in a system and there are no outside forces, the total energy should stay the same. Absolutely no difference when we look at law of conservation of energy when we're talking about rotational motion. All this means is that, hey, we're adding another type of energy. So what have we looked at this year? Well, we first looked at gravitational potential energy and translational kinetic energy. First semester, we only looked at those two types of energy in a system. We moved into second semester, did simple harmonic motion, and we also talked about spring energy. And so at that point, we said when you do law of conservation of energy, you need to consider the three different types of energy. And now, as we add in rotational kinetic energy, you now have to consider whether or not there is a rotating object in your system or not. And you have to include that energy in your system if necessary. Now, another thing to consider is that if we had an object that was changing its translational kinetic energy, we were able to set that equal to the work done on the object, and we did the force multiplied by the distance that that force was applied for. That allowed us to solve for different things, um, in some cases by determining what forces were, doing Fermat. It can be a useful thing to know at times. There can also be cases where if we change the rotation of an object, then we're changing the rotational kinetic energy. And that has to be equal to work as well. And just like we look at the variables from linear motion and compare them to rotational motion, when we find the work in changing the rotational kinetic energy, instead of looking at just force, we're going to look at the torque that's applied. Instead of looking at the distance, we're going to look at how much the angular position changes. So for instance, if you apply a constant torque as the object completes an entire circle, one rotation, you would take that torque, you would have to calculate it by doing F perpendicular to R, and then multiply by a delta theta of 2 pi. And that would calculate how many joules of work were done in changing the rotation of the object. But bottom line is, don't do anything very differently from what we were doing before with energy. Just know that there is a new type of energy, rotational kinetic energy, and that the work done in changing the rotation can be calculated by doing torque multiplied by delta theta. So that's it for rotational energy.